Hello everyone and welcome back to the video lecture series for Calculus 1. Today we are going to be discussing a concept called continuity. So intuitively, a continuous function is one whose graph can be traced from left to right with a pencil without ever having to lift up your pencil. Meaning a continuous function contains no holes, no jumps, no breaks, no asymptotes, nothing like that. So there are going to be times when the entire graph is continuous. Now, sometimes, as is the case with many piecewise functions, only part of the graph is continuous, and there may be points or intervals of what are called discontinuity. Discontinuity occurs when you're tracing it and you have to lift up your pencil because you encountered a hole, jump, break, asymptote, or whatever. There is a more precise definition of continuity, and it is actually going to involve limits. But first, let's take a look at an example of a continuous function and an example of a function that is not entirely continuous. So for this first one, if you were to trace this from left to right, you will notice that you never have to lift up your pencil. So this is an example where the entire graph is continuous. Now, overall, the entire graph for this next one is not continuous, but it does have moments where it is continuous. So for this first section right here that I've just traced, that was all continuous because I didn't have to lift up my pencil until I got to here. So 15, because I had to lift up my pencil to get to the next point, 15 is a point of discontinuity. Then I've got a continuous interval again until I get to 30, and 30 is another point of discontinuity. Then I've got another interval of continuity until I get to 45, another point of discontinuity, and then you get the idea. So definitely write these down because you will be directly tested on determining continuity at a point. So in order for a function f of x to be continuous at a point x equals a, there are three conditions that need to be met. And all three conditions need to be met in order for a function to be continuous at x equals a. So the first criteria is that f of a needs to be defined, meaning that a needs to be in the domain of f of a needs to be defined. Also, the limit as x approaches a of f of x needs to exist, meaning both the limit from the left and the limit from the right need to equal each other, and they need to equal the same value, and the limit can't come out to 1 of the infinity. So the limit needs to exist and be a real number. And then the third criteria is that the limit as x approaches a of f of x needs to equal f of a. So the limit needs to equal the function's value. Now, all three of those conditions need to be met in order for a point x equals a to be continuous. Now, if one or more of these conditions fails, then we say that f of x has a point of discontinuity at x equals a. And it doesn't matter which criteria it fails. If it fails even one of them, it is automatically a point of discontinuity. So we're going to take a look at this graph on the open interval 0 to 7. And we're going to identify the values where f has a discontinuity. And more importantly, we're going to state why there is a point of discontinuity. So obviously there's a lot of them, so let's just go from left to right. So from left to right, the first point of discontinuity that we run into is 1. So the reason why 1 is a point of discontinuity is because f of 1 is undefined. 1 is not in the domain, it is a hole, so x equals 1 is a point of discontinuity because it fails that first condition. Next point of discontinuity that we run into is x equals 2. And let's just go through the criteria. So is f of 2 defined? Technically, yes, f of 2 is defined. It's up here at 3. Does the limit as x approaches 2 exist? Well, coming from the left and coming from the right, this graph is approaching 1. So yes, the limit does exist. But the function's value does not equal the function's limit. So it actually fails condition 3. The limit as x approaches 2 does not equal f of 2. So that's why x equals 2 is a point of discontinuity. Now x equals 3 is another point of discontinuity because even though f of 3 does exist, The limit as x approaches 3 does not exist because from the left it is approaching 2, from the right it is approaching 1. So overall, the limit as x approaches 3 does not exist. Next point we actually run into is 5. 5 is a horizontal asymptote. Horizontal asymptotes are points of discontinuity because f of 5 is undefined. Now, everything between 3 and 5 was all continuity. So it had an interval of continuity between 3 and 5, and then again between 5 and 7. It had a little mini interval of continuity between 0 and 1, and then between 1 and 2, between 2 and 3. But these are all of the points of discontinuity. It's continuous everywhere but these 4 points. So what we're going to do is we are going to run through the continuity criteria, and we're going to determine whether these functions are continuous at the point in question. And if they are, we're going to justify it by going through all 3 continuity criteria and showing that it does fit all 3 continuity criteria. And then if it's not, we're going to state which criteria it fails. So our first function is 3x squared plus 2x plus 1 over x minus 1. And then we're looking at the point 1. So let's start with f of 1. Well, if you plug in 1, you get a 0 in the denominator, so f of 1 is undefined. So because f of 1 is undefined, it's automatically a point of discontinuity, so it is not continuous at x equals 1. Because f of 1 is undefined, we don't even need to check the other 2 criteria because remember, if it fails even one of them, it's automatically a point of discontinuity and we get to move on. Now for the next one, we got the same function, but this time we're looking at x equals 2. So let's check g of 2. So g of 2 is defined, but you really should check to, see what g of 2 actually is because it's going to be a little bit more involved than that. So if you were to plug 2 into every single spot that you see this function, you would actually get 17. So g of 2 obviously exists. So then let's take the limit as x approaches 2 of g of x. Remember, whenever you're taking a limit, you should always try direct substitution first. I know that we kind of, got off the rails there with the infinities with the direct substitution, but you should always try it first. So if you actually do direct substitution, you get 17. So the limit exists. And if you notice, these two are the same values. So the limit as x approaches 2 of g of x actually equals g of 2. So the limit equals the function's value. So criteria 1 met, criteria 2 is met, criteria 3 is also met. So therefore, this function is continuous at x equals 2. So then for this third one, let's go through the continuity criteria. Now, this function is a piecewise function, and it is going to behave like the function x times the sine of 1 over x if x is not equal to 0. And it is going to take on a value of exactly 0 if x is equal to 0. So let's go through the continuity criteria. Let's just check h of 0 first. So the y-coordinate that goes with an x-coordinate of 0 is 0. So h of 0 is actually equal to 0. Next, we're going to take the limit as x approaches 0 of our h of x. Now, remember, a limit is what is going on near a point, not at the point. So this is what it's doing at 0. The limit as x approaches 0 is asking, what is it doing everywhere else besides 0? What is it doing at points near 0, not at 0? Well, near 0, it's actually going to take on this behavior here as x times the sine of 1 over x. So we're going to take the limit as x approaches 0 of x times the sine of 1 over x. Now, because this video is going to be long as it is, this is a long section, this is actually going to involve the squeeze theorem. So go ahead and use the squeeze theorem to find this limit here. You should get 0. So h of 0 exists. the limit as x approaches 0 of h of x exists. And you will also notice that the limit as x approaches 0 of h of x does indeed equal h of 0. So what this means is that this function is continuous at x equals 0. It fulfills all three continuity criteria. So let's say that you have two continuous functions f and g. And if you take two continuous functions, you can do all of these operations to them and still get a continuous function. So you can add or subtract two continuous functions and still get something that's continuous. You can take a continuous function and multiply it by a constant, and that will also be continuous. You can take two continuous functions and multiply them, and its product is continuous. Now, you can take two continuous functions and divide them, and the quotient will be continuous as long as the denominator does not come out to 0. So the quotient of two continuous functions is continuous for every value that does not make the denominator 0. Then you can take a continuous function and raise it to an integer power n, and it will be continuous. You can also compose two continuous functions, and the composition will be continuous. Now, polynomials are always continuous because every single polynomial that exists is a smooth, unbroken curve with no holes, jumps, breaks, asymptotes, or anything else weird. So polynomial functions are always continuous for all values of x. So polynomial functions are continuous for all real numbers. Also, saying that a function is continuous because it's a polynomial is completely acceptable. That's a totally acceptable justification because polynomials are always continuous for every value of x. Now, rational functions, which are just the quotient of two polynomials, are continuous for all values of x where the denominator is not equal to 0. So basically, rational functions are continuous on their domains. That means that any point that is not in the domain of a rational function is automatically a point of discontinuity. But all other points besides those that would make the denominator 0 are points of continuity for a rational function. So what we're going to do is we're going to take this rational function and we are going to determine the values of x where this function is continuous. So since this is a rational function, that will mean it is continuous on its domain. So it will be continuous for all x's except the ones that make the denominator 0. So let's first figure out the points of discontinuity, and then we'll work on where it is continuous. So it has discontinuities at any point where the denominator, x squared minus 7x plus 12, is equal to 0. So if you were to just factor this really quick, it would factor as x minus 4 times x minus 3. So the 2 points of discontinuity are going to be x equals 3 and x equals 4. That's it. Those are the only 2 points of discontinuity because those were the only 2 points that are excluded from the domain. So because the domain is everything but these 2 points, that means this function is continuous at every single value of x except these 2. So that is obviously a lot of points of continuity. So what we're going to do is we are going to express that as what is called an interval of continuity. What an interval of continuity will be is it will say, okay, this function is continuous everywhere except x equals 3 and x equals 4. So obviously, this function is going to be continuous for all values that are less than 3. So it is going to be continuous on the interval negative infinity to 3. However, infinity is not a number, so it gets a parenthesis. 3 is a point of discontinuity, so we are not going to include it in our interval of continuity, so it too is going to get a parenthesis. Then it is going to be continuous for every value between 3 and 4. So it is going to be continuous on the interval from 3 to 4. Again, 3 is not included, 4 is not included, so they both get parentheses. And then it is going to be continuous for all values that are greater than 4, just not 4 itself. So it is going to be continuous on the interval from 4 to infinity, and both 4 and infinity are going to get parentheses. So that is an interval of continuity, and it's just stating all values where this function is continuous. So then for this next one, for what values of x is this function continuous? Now think before you just jump in. So we have a rational function inside the parentheses. Rational functions are continuous on their domains, which means that rational functions are continuous for all values of x except the points where the denominator is equal to 0. Well, if you take a look at this denominator, is this denominator ever equal to 0? No, because x to the 6th plus x to the 4th plus 1, this denominator is never equal to 0. So because this denominator never equals 0, that means this entire inside function is never undefined, which means that entire inside function is continuous for all real numbers. Then if you take a continuous function and raise it to an integer power, that is still continuous, and it's still continuous on all real numbers. So for what values is this continuous? All real numbers, also known as the interval between negative infinity and infinity. Now, because it's continuous, that means direct substitution will work when you're finding any limit as x approaches a finite number. So if you were to take the limit as x approaches 0, because this function is continuous, you can direct substitute. That's why direct substitution works. If you are taking the limit as x approaches a point of continuity, that means the function's limit will always equal the function's value. So that's why when you have a point of continuity in your limit, direct substitution is going to work because it will meet that third criteria. So if you direct substitute, you actually get 1024 for this limit. Now, for intervals of continuity, like we saw with the rational function, it was just plainly discontinuous at 3 and 4 because 3 and 4 were actually vertical asymptotes. Now, when especially you have a piecewise function where you have breaks involved, you can have a function that is continuous from one side or the other. Even if it's a point of discontinuity overall, it might be continuous from the left or continuous from the right. Now, a function is continuous on an entire interval if it is continuous at every single point in that interval, such as that 4 to infinity interval. Now, a function is left continuous or continuous from the left if the limit as x approaches a from only the left is actually equal to f of a. A function is right continuous or continuous from the right if the limit as x approaches a only from the right equals f of a. So what we're going to do for each of these, just by looking at their graphs, we're going to determine the intervals of continuity for each of these. So it is obviously going to be continuous between a and b, because for every single point between a and b, this is a smooth, unbroken curve. Now the question is, does it have one-sided continuity, and can we include one of these two endpoints? So let's take a look at a. The limit only exists from the right. So the limit as x approaches a from the right does actually equal f of a. So this function is continuous from the right of a, so a has one-sided continuity, so I'm going to include it with a bracket. Now the limit as x approaches b, yes, it only exists from the left, but the limit as x approaches b does not actually equal f of b because f of b is undefined, so that is going to get a parenthesis. So that's going to be pretty much the same idea for this next one. Between a and b, it is a smooth, unbroken curve. Now, if you take the limit as x approaches a from the right, it does not equal f of a because f of a is undefined, so I'm going to give it a parenthesis. It is not a point of continuity. However, the limit as x approaches b from the left does equal f of b, so b is continuous from the left, so I'm going to give it a bracket. One-sided continuity is going to come in a lot with piecewise functions. So we've got this function here. It's going to behave like the quadratic x squared plus 1 for all x's that are less than or equal to 0. And then it is going to behave like the linear function 3x plus 5 for all x's that are greater than 0. Now, if you take a look at each individual piece, we're supposed to determine the intervals of continuity. Each individual piece is a polynomial. So each individual piece is a smooth, unbroken curve. So since they're both polynomials, the only potential point of discontinuity would be x equals 0, which is where the two pieces break apart. Now, if the two pieces connect, then the whole thing's going to be continuous. However, if the pieces do not connect, you're going to have a point of discontinuity at x equals 0. So let's figure out if x equals 0 is a point of continuity. If it is, then it's continuous for all real numbers. If it's not, since this is the only potential point of discontinuity, that would be our only point of discontinuity. So let's go through the continuity criteria. Let's start with f of 0. Now, remember, you can only plug this into one piece. This top piece is defined for x's that are less than or equal to 0. So to find f of 0, I'm actually going to plug it into the top piece. 0 squared plus 1 gives us 1. So f of 0 is equal to 1. Next, we're going to find the limit as x approaches 0 of f of x. Now, because we are taking the limit of a piecewise function at a breaking point, you might remember from a few videos ago that you have to take each one-sided limit individually. So because it breaks apart, we do have to find the limit as x approaches 0 from the left and x approaches 0 from the right. So let's start with the limit as x approaches 0 from the left of f of x. So from the left, values to the left of 0 are less than 0. So I'm going to be plugging it into the top piece since the top piece is defined for x's that are less than 0. So I'm going to have direct substitute only into that top piece. So I get 0 squared plus 1, which is 1. Then for taking the limit as x approaches 0 from the right of f of x, I am going to be plugging it into the bottom piece here. So because from the right of 0, we're going to be looking at values that are greater than 0, and this bottom piece is defined for all x's that are greater than 0. So I'm going to direct substitute into the bottom piece, which gives us a limit from the right of 5. So because the limit from the left does not equal the limit from the right, that means the overall two-sided limit does not exist. So because it failed the second continuity criteria, that means that the x equals 0 is a point of discontinuity. Because it just failed the second criteria, the limit as x approaches 0 does not exist. However, if you notice, the limit as x approaches 0 from the left does actually equal f of 0. This right here actually equals f of 0. So because the limit as x approaches 0 from the left did equal f of 0, that means this function is continuous from the left. So because it's left continuous, in our interval of continuity, yes, overall, x equals 0 is a point of discontinuity, but we're going to represent this continuity from the left in our interval. Now, because the limit as x approaches 0 from the right did not equal f of 0, it is not continuous from the right. So here we go. So here's our interval of continuity. it is going to be continuous for all values that are less than 0. So it is going to be continuous on the interval from negative infinity to 0. However, because it was continuous from the left, that means from the left is values less than 0. I'm going to give this interval a bracket because it was continuous from the left. It is not continuous at 0, so this interval does need to break apart at 0. And it is going to be continuous on the interval from 0 to infinity. Now, because this function was not continuous from the right, on this interval from infinity to 0, from 0 to infinity, 0 is actually going to get a parenthesis. So that is going to be our interval of continuity, with a bracket here from the left, but a parenthesis here from the right. Now, when you have continuity with roots, the type of root will determine your continuity. So if you have a continuous function and you are raising it to some sort of rational exponent that involves an odd root, such as taking the cube root of a continuous function, there are no domain issues with odd roots. Like, you can take the cube root of a negative number and not run into any issue. So if you take the odd root of a continuous function, it is going to be continuous at all points for which f is continuous. Now, if you are taking an even root, that's going to be different because you can't take the square root of a negative number. So if you have an even root of a function, it's going to be continuous at all points for which f is continuous and where f is positive. So basically, these type of compositions that involve roots are going to be continuous on their domains. Radical functions are also continuous on their domains. So then, we're going to figure out for what values are each of these functions continuous. So we have the square root of 9 minus x squared. Now, 9 minus x squared, if you take a look at the inside function, that's a polynomial. That's going to be continuous for all real numbers. That means this composition with the square root will be continuous as long as whatever is inside the square root, 9 minus x squared, is greater than 0. So what that means is that between negative 3 and 3, this function is going to be continuous. Now, as far as whether it's continuous at the endpoints, you can take the square root of 0. So because you can take the square root of 0, you can actually plug in the endpoints and still get a real number. So it is going to be continuous between negative 3 and 3 included. And if you take a look at this, if you can recognize what type of graph this is actually going to be a semicircle with a center of 0, 0 and a radius of 3. You will see that at negative 3, it is going to be continuous from the right. At positive 3, it is going to be continuous from the left. So your interval of continuity is going to be negative 3 to 3, including both negative 3 and 3. Now, unfortunately, that's the only interval of continuity, because the graph doesn't even exist outside of the semicircle, and this composition is only continuous where the inside function is greater than 0. Now, for the next one, think very carefully before you just dive into this one. Take a look at what's in the parentheses, x squared minus 2x plus 4. It's a polynomial, it's continuous. And we're taking that and raising it to the power of 2/3. So the 2 in the numerator means we're squaring it. You can take a continuous function and square it, and it's still continuous. This 3 in the denominator indicates what type of root you are taking. So we are taking essentially the cube root of x squared minus 2x plus 4 squared. Odd roots don't have any domain problems. You can take the odd root of a negative number. So we took a continuous function, squared it, still continuous. We took that continuous function and then took its cube root, means it's still continuous. So this entire composition here is continuous for all real numbers. So the interval of continuity for this one is actually going to be all real numbers, negative infinity to infinity. And in fact, all of these functions are going to be continuous on their domains. which means any point that is not in the domain of any of these functions is automatically a point of discontinuity, but that's it. Any point that's not in the domain is the only points of discontinuity. So sine and cosine, for example. Because the domains of sine and cosine are all real numbers, that means sine and cosine are continuous for all real numbers. And if you remember their graphs, they are smooth, unbroken curves from negative infinity to infinity. Now, tangent obviously has a lot of vertical asymptotes, but those are all points that are not in the domain of tangent. So, pi over 2, for example, where tangent is undefined, that means that that's a point of discontinuity. But those are going to be the only points of discontinuity. So tangent is going to be continuous on its domain. In fact, all of the trig functions are continuous on their domains. Now, even though, especially for sine inverse and cosine inverse, their domains are limited, the inverse trig functions are also continuous on their domains. The exponential functions are also continuous on their domains, and because the domain of an exponential function is all real numbers, that means exponential functions are continuous for all real numbers. So e to the x is continuous for all real numbers, and any other base b to the x is also continuous for all real numbers. And the logarithmic functions, both the natural log of x and for log base b of x, these are both going to be continuous functions on their domain. So yes, you cannot take the log of 0, you can't take the log of a negative, but as long as it's on its domain, they're going to be continuous on their domains. So we're going to determine the continuity of this function, and we're going to evaluate its limit. So if you take a close look at this function first, we are taking cosine. Let's take a look at the numerator. We're taking cosine, which is a continuous function, and we are squaring it, which is still continuous, minus a constant 1. It's continuous. Then in the denominator, we're taking a continuous function cosine, minus 1, still continuous. So both numerator and denominator are continuous for all values of x, which means that the overall quotient is going to be continuous except where the denominator is equal to 1. Sorry, where the denominator is equal to 0. So this is going to be continuous for all points x except where the denominator, cosine x minus 1, is equal to 0. That means it's going to be continuous at every point except where the cosine of x is equal to 1. So it's not going to be continuous at 0. It's not going to be continuous at 2 pi. It's not going to be continuous at 4 pi. It's not going to be continuous at negative 2 pi or negative 4 pi, and so on and so forth. So we're just going to say that this function is not going to be continuous for all integer multiples of 2 pi. Because on the unit circle, this overall quotient is not going to be continuous at that point right there, or any point that is coterminal to it. So it's not going to be continuous for all integer multiples of 2 pi. Now, that means when we're taking the limit as x approaches 0 of this function, 0 is a point of discontinuity, so direct substitution won't work. But you should always try direct substitution just to see what kind of situation you have. Because remember, 0 over 0 is treated a lot differently than any other number over 0. Actually, if you direct substitution actually gives you 0 over 0. And I did promise that any 0 over 0 can be handled by either factoring or rationalizing. I don't see any square roots, so I'm going to try factoring. If you take a look at the numerator, cosine squared minus 1, that's actually a difference of squares. So you can actually factor the numerator as cosine of x minus 1 times the cosine of x plus 1. Then the denominator is just going to be cosine of x minus 1. There's that common factor that was causing the 0 over 0, so I'm going to cancel that out, leaving me with the limit as x approaches 0 of the cosine of x plus 1. So then I'm going to direct substitute again. The cosine of 0 is 1. 1 plus 1 gives me a limit of 2. So I do want to point out, yes, the limit existed. Yes, we got the real number 2. But this is still a point of discontinuity because the function is still undefined at 0. Now, something like that is actually what is going to be called a removable discontinuity. Removable discontinuities occur in very specific cases. So let's say, like in the last problem, the limit as x approaches some value c exists, but is not equal to f of c, mostly because f of c is undefined. That means we have a hole at x equals c, and that means it is a removable discontinuity. So these types of discontinuities can be continuous. They can be made continuous by redefining f of c. So let's take a look at this function first. What we're going to do is we are going to state the domain of this function, and we're going to state any points of discontinuity. So let's start with the points of discontinuity. This is a rational function, a polynomial divided by another polynomial. Rational functions are going to be continuous on their domains, so it is going to be continuous at every point except where the denominator is equal to 0. So the possible points of discontinuity are x equals -3 and x equals 3. So its domain is going to be all real numbers except -3 and 3. So its domain is going to be from -infinity to -3, from -3 to 3, and then from 3 to infinity. And these are the only points of discontinuity, because they are the only points that are excluded from the domain. Rational functions are continuous on their domains. Any point that's not in the domain is a point of discontinuity. Now, I can't do two things at once in these videos. If I try to toggle over to a graphing calculator, it will probably crash this computer. So what I want you guys to do on your own is I want you guys to graph this function on your graphing calculator. Don't forget to put parentheses around the numerator and the denominator. And I want you to actually look at the graph and see what is going on at x equals 3 and x equals -3. You might have to look in the table of values. You will notice that one of them is an asymptote and one of them is a hole. The hole is a removable discontinuity because what we can do is we can redefine this function by redefining f of c to, quote, fill in the hole. So again, I want you guys to look at that graph on your own time. We're going to look at how to see this algebraically because you can actually see removable discontinuities without even having to touch a graphing calculator. You can see them algebraically. If you looked at the function on your graphing calculator, you would notice that x equals 3 is the hole. And if you were to actually take the limit as x approaches 3 using direct substitution, you get 0 over 0. So 0 over 0 means that this is a removable discontinuity, also known as a hole. Now I've gone ahead and factored it for you just for the sake of time. So now that I have it factored, you will notice where the factor that is causing that 0 over 0 is. There's that common factor that is causing the 0 over 0. So now if you take the limit as x approaches 3, you are actually going to get, again, we're going to try direct substitution. We're going to get 3 plus 2 times 3 plus 1 all over 3 plus 3, which gives us 20 over 6, which reduces to 10 over 3. So the limit exists. We clearly got a real number for the limit. But f of 3 is still undefined. You saw that from the graph. That is indisputable. F of 3 is undefined. But because f of 3 is undefined and the limit exists, that means there is a hole at the point 3 comma 10 over 3, and it is a removable discontinuity. Now, a removable discontinuity, we're not actually going to change the function. What we're going to do is we're going to write a brand new function called a continuous extension. A continuous extension is a brand new function. It is going to be a piecewise function that redefines f of 3. So this new piecewise function is going to replicate all of the exact same behavior as the original function, except at the removable discontinuity x equals 3. Essentially what we are doing is we are creating a carbon copy of the original function with an additional point placed right above the hole, which will in essence fill the hole. Now, I also want to note that x equals -3, which you saw from the graph, is not a removable discontinuity because it was a vertical asymptote. Vertical asymptotes, their limits come out to infinity. That's not a real number, so the asymptotes are not removable discontinuities. You are stuck with them. So the continuous extension of f of x will replicate all of the exact same behavior as the original function, x cubed minus 7x minus 6, all over x squared minus 9, for all x's that are not equal to 3. So it will replicate all of the same behavior if x is not equal to 3. Then it is going to take on a value of exactly 10 over 3, which was its limit, if the function is if x is equal to 3. So again, carbon copy of the original function here for this top piece, with an additional point placed directly above the hole for this second piece, and then this brand new function, this continuous extension, is now continuous at x equals 3. Now, another really important theorem that involves continuity is called the intermediate value theorem. There are going to be 3 main theorems in this course that are going to be kind of cornerstones for this course. They're called the intermediate value theorem, the mean value theorem, and the fundamental theorem of calculus. So we'll get to those other 2 in a little bit, but the intermediate value theorem states that, let's say you have a continuous function f, and suppose f is continuous on a closed interval a to b. And L is some number, some value between f of a and f of b. So L is some y-coordinate between the endpoints. Then there is at least one value c between a and b where f of c is equal to L. In plain English, that means that if a function is continuous on a closed interval, it takes on every single value between the endpoints at least once. So it is a theorem that is kind of stating the obvious. So again, we have a closed interval, a to b. The function is continuous on that entire interval. That means every single y-coordinate between the 2 endpoints has a corresponding x-coordinate at least once. So what this means is that every single y value between f of a and f of b will occur at least once. So in this case, we have exactly one value between c, between the endpoints a and b, that has a y-coordinate L. Now, it did say at least one, so it doesn't guarantee just one. So this is an example. This second graph over here is an example where we have a value L between the endpoints, where we get the y-coordinate L 3 times in our interval a to b. Now, the key, in order to use the mean value theorem, there are actually 2 conditions that need to be met. The function needs to be continuous, and the interval needs to be closed. Both of these were continuous, and the interval was closed, meaning both endpoints need to be defined and included in order for this to work. So here's an application of the intermediate value theorem and how you would use it. So let's say that the function, we're going to show that the function x cubed plus x plus 1 has at least one 0 on the interval -1 to 1. So let's check to make sure that we can even use the intermediate value theorem before we can jump into it. So first condition, is this function continuous? Is f of x continuous? Yes, because it's a polynomial. And is the interval closed? Yes. So because we have a continuous function on a closed interval, that means the intermediate value theorem applies. So the intermediate value theorem says that this function will take on every single y-coordinate between the endpoints at least once. So let's actually see what's going on at the endpoints, since the intermediate value theorem involves the endpoints. So let's actually find f of -1 and f of 1. So if you plug in -1 into every single spot that you see an x, you actually get -1. And if you plug in 1, you get 3. Now we're supposed to show that this function has at least one 0. The 0 of a function is where the function actually takes on a value of 0. So it's just saying show that this function equals 0 at least once in this interval. Well, one endpoint has a negative y-coordinate, which is below the x-axis. The other endpoint has a positive y-coordinate, which is above the x-axis. This is a continuous function. It's a smooth, unbroken curve. If you have a smooth, unbroken curve and you start from below the x-axis and you end up above the x-axis, that means you have to cross the x-axis at least once. Because the only way that you can have a smooth, unbroken curve and go from a negative number to a positive number is to cross 0 at least once. So let's state that. So because f of -1 is less than 0 and f of 1 is greater than 0, by the intermediate value theorem, IVT is perfectly fine for shorthand. By the intermediate value theorem, f of x is equal to 0 at least once. We don't know how many times it crosses the x-axis. We just know that it has to cross the x-axis at least once in order to go from a negative value to a positive value. And this just doesn't just have to do with negatives and positives and zeros. You can use the intermediate value theorem to just show that every single y-coordinate between the endpoints will have a corresponding x-coordinate at least once. So for this next one, let's say that you invest $1,000 in a special 5-year savings account with a fixed annual interest rate R that is compounded monthly. The amount of money, A of R, in the account after 5 years is given by this function here. So what we're going to do is we are going to show that there is a value of R, I'm sorry, that's a typo right there. There is a value of R between 0 and 0.08 where A of R equals 1400. So what we're essentially going to do is we are going to use the mean value theorem to show that there is at least one interest rate between 0% and 8% that yields an account balance of exactly $1,400. So before we use the intermediate value theorem, let's make sure that we can actually use it. So let's just make sure that it applies. So first of all, is this function continuous? So this is actually a polynomial because you have R, which is divided by 12 plus 1 raised to the power 60. 60 is an integer power times 1,000. This is actually a polynomial of degree 60. And now that I fixed that little typo there, the function is continuous because it's a polynomial and the interval is closed. So yes, the intermediate value theorem does apply. Because the intermediate value theorem applies, we can use it. So let's actually see what's going on at the endpoint. So we're going to find A of 0 and we're going to find A of 0.08. So I'll plug in 0 for R and you actually get 1,000. Then if you plug in 0.08 for r, it's not going to be very pretty, but you get approximately $1,489.85. So a of 0 was 1,000, which is less than 1,400. A of 0.08 is a number that is greater than 1,400. Because this is a smooth, unbroken curve, that means that this function needs to take on every single y-coordinate between 1,000 and 1,489 at least once. So, because a of 0 is less than 1,400, and a of 0.08 is greater than 1,400, by the intermediate value theorem, that means that there is at least one interest rate R that gives an account balance of $1,400. So that means A of R equals 1,400 at least once. There is at least one interest rate between 0 and 8% that gives an account balance of exactly 1,400. So that is going to be it for continuity, and that is actually going to be it for this chapter. So starting in the next chapter, we are going to start in with derivatives, and we're going to pretty much stay in derivatives for the next big portion of this course. So thank you all very much for watching, and I will see you in the next video for derivatives. Bye-bye.